Today, we are going to do our introduction to acids and bases. The next part of this unit, which we pick up on next week, is strength of acids and bases. So there's a difference between the strength of an acid and base and its concentration. Okay, and we're going to talk about what that is next week. Then we're going to talk about what pH is. You've probably heard of pH before as far as like if something's an acid or a base. I'm sure you've heard of the terms acid and base, especially acid. Okay. And then we get into something called titration. So you've probably seen these really long tubular like pieces of glassware that I've had in the back room all year, several times out for AP labs. You guys are going to get your try at those next week. So, all right. So introduction. So acids and bases. Acids are going to taste sour, and you may have experienced that in a few different places like soda, lemons, limes, oranges, any kind of citric fruit. That's where they get citric acid from because it shows up in citric fruits or citrus fruits. And then acetic acid is your vinegar. So balsamic vinegar, apple vinegar, all those different types of vinegar that we have out there, you would have experienced acetic acid in those. Okay. And you guys learn to write some of these formulas at the beginning of the year or middle of the year. Remember, these are all going to start with H's. Okay. And then carbonic came from what ending? It came from 8. So you would find carbon 8. Okay. This had a -2 charge. This was a +1. So there is the formula for carbonic acid. Acetic acid would have come from acetate. Okay, acetate is that. It has a -1 charge. This is a +1. So remember how to write those formulas for your different acids. Citric acid is a little different. We're not going to worry about that guy. All right. Basic solutions then are going to taste bitter and they feel slippery. Okay. Have you ever gotten like a little bit of shampoo in your mouth? Maybe your parents washed your mouth out with soap when you were a kid. That's becoming less and less common, but back in my day, yeah. Huh?
Thank goodness. That sounds horrible. My mom used vinegar.
You don't say naughty words, do you? You learned your lesson. Exactly.
Well, no, it's not that I said naughty words. I was just sassy.
Oh, well, there's that too. But you guys, maybe you've seen Christmas Story where the life boy, part of it. It's funny. All right. Anyway, reactions. Acids will react with some metals in single replacement reactions. They're going to produce hydrogen gas. And remember that all of your acid formulas are going to start with H. Okay. And then acids also react with some things to form carbonates. Or they sometimes produce carbon dioxide gas.
Oh wait, we got the wrong thing.
All right, good?
I'm confused on what to write.
Okay, so they're going to react with some carbonates. And So it produces carbon dioxide gas. React with some models to form hydrogen gas. I don't know. Just leave them blank. I'm tired and it won't be on the test anyway. Well, there is no test. Well, there's a final. Okay. Anyway. So, acetic solutions, you're going to have in the, so you've got a liquid here. Okay. This is the whole idea behind an acid. Okay. And in that solution, you're going to have some hydrogen ions floating around. And if you have more hydrogen ions floating around than you have hydroxide ions, then you've got an acidic solution. All right. You could also swing the other direction. So you could end up with having more hydroxide ions than you have hydrogen ions. And then you would have a basic solution. If you have an equal amount of both, then what kind do you have? What do you think that's called?
Water?
And water has what? What is water considered as far as acid or base?
Neutral.
Neutral, right.
Oh, good.
That is where you're going to have your, good Lord, that's ugly. Let's try that again. That's where you're going to have your H plus equaling your OH minus. So those amounts will equal one another. And that's called a neutral solution. Now in biology, they generally consider neutral as anything between 6 and 8 for a pH. In here, we're a hard 7. Anything above that is a base, anything below that is an acid. You're right at 7 in here. We're much more exacting than that. All right, we have some definitions that we're going to go through. The first gentleman that we're going to talk about is Arrhenius. And Arrhenius said that your acids are going to produce H plus ions. So here's an example of that. And your bases will produce OH ions. So here's an example of that. Okay. The problem is that with his model, there's certain things like ammonia here. Ammonia is a common base, but it doesn't produce hydroxide ions. It can't. It doesn't have any oxygen in it. So that's where his concept kind of fell apart and people no longer used his definition. All right. In the 1920s, though, Bronsted and Lowry came up with another definition. And they said that the acids would donate hydrogen ions and the bases are going to take them. So one is a donor and one is an acceptor. Good.
So only focus on oh. On here it says Bronsted and Lowry decided to focus only on the blank compounds.
Hydrogen.
Okay. No, that's not this.
All right, Bronsted Lowry then. We're going to look at an acid. Okay. If this guy was placed in water, so hydrochloric acid was placed in water, this hydrogen here is going to get donated from here and come over to here. That would make this H3O plus and leave this guy behind without chlorine. All right. So the way I tell people to find these is I tell them to find the things that look like they belong together. Okay. Like they're pairs. Okay. Or siblings. All right. You know how siblings tend to look like one another. So do you see how this guy right here looks similar to this guy? He's just lacking a hydrogen. Then I tell people find the one that has more hydrogen in it. So this guy has more hydrogen out of those pairs. This one has more hydrogen. So this is going to be my acid, and this would be my base. But if it's on this side, we call that a conjugate base. So we're going to call that a CB on this side. Do you see how these two look very similar to one another? They're only different by one hydrogen. Which one has more hydrogen? This guy. So he's going to be my acid, and this would be my base. And I distinguish this side of the equation as a conjugate. So conjugate acid. All right. Okay, that's right. Okay, so Bronsted Lowry. We are going to look at a base here. So here, do you see how this guy and this guy look similar to one another? Which one has more hydrogen? This guy. So he's my acid, he's my base, but he's on this side, so we're going to call him conjugate. Now this may not look obvious, but remember back in the day when we were balancing equations, we could write that guy as HOH. Do you remember doing that? So if this guy is written as HOH, can you see how those are similar to one another now? All right. So then which one has more hydrogen? This guy. This is my base. He's on this side, so I'm going to call him a conjugate. Make sense? Happy? Good? Making sense? Easy enough? Find the pairs. More hydrogen acid, less hydrogen base. All right, so let's try here. We're going to find our pairing. Can you find the pairings here in this guy? Maybe think of this as HOH. Which one has more hydrogen? This guy. This one has less hydrogen. It's on this side, so we call it a conjugate. Between these two, which one has more hydrogen? This guy. Which one has less hydrogen? This guy. This guy is on this side, so we call it a conjugate. So see if you can do the next two. Do it. Need more time? All right. So I found my pairings. This one has more hydrogen. This one has less. On this side, I call it a conjugate. This is HOH, more hydrogen, less hydrogen. It's on this side, I call it a conjugate. Over here, pairings again. More hydrogen, less hydrogen. Over here, more hydrogen, less hydrogen. This is my conjugate. Easy enough? Now, there are certain situations where water, and there's other things too, but water is a great example of this, where sometimes it acts as an acid in certain situations, and in other situations it acts as a base. Okay? And we call that amphoteric. So remember, ampho or amphi means that it has two identities. So like your amphibians, they live in what?
Land and water.
Land and water. Okay? So if something's amphibious, it has two different places that it lives. So water can act as an acid or a base. There's certain things that can do that. Other things like hydrochloric acid, not an option. Okay? But certain things can. And so that's where they get that term amphoteric. All right. Last slide. We have things called monoprotic acids, and we have things called polyprotic. So monoprotic means that it can only donate one hydrogen. That's all it has to give. Polyprotic can donate more than one hydrogen. So here it would have two. Here it would have two. This guy would actually have three. So what do you see about the formulas differences between monoprotic and polyprotic?
Monoprotic only has one hydrogen. Polyprotic has multiple.
Right. You're going to have a subscript down here for any of your polyproducts for your hydrogen. Okay. Easy enough? All right. That's it for today.